Hey folks, this will hopefully be a quick video on rotational work and energy. What we're going to do right now is imagine that there's a pulley with a rope tied around it, and that the rope is going to be pulled with a force, and that force is going to cause this point on the pulley to move a specific distance. And because of the way ropes attach to pulleys, I can say that the distance that any point along the rope moves is equal to the distance that a point on the outside of the pulley moves. So if I move the force a distance s, that distance is matched on the outside of the pulley. So we'll just imagine like pulling it so that the pulley rotates 90 degrees. That's an angular displacement theta. And a linear displacement s. So I have done work on the outside of that pulley, and that work is equal to FD cosine theta, as we've talked about, which in this case is equal to the force times the distance that the outside of the pulley has moved. Because of the relationship between linear and angular variables, I can use one of our first translations, and I can say that the work done on the outside of this pulley is equal to the force that's been applied times the radius of the pulley times the angle through which the pulley has rotated. These two variables we know go together, and so the work that's done to rotate the pulley, I don't know why I said it like that, is equal to the torque applied times the angular displacement. So we have an analog here again, that we have linear work done on the rope that is then transferred to the outside of the pulley, and that work caused an angular displacement, and so the rotational work is the torque times the angular displacement. This is in joules because it is work. Okay. The idea behind work is that it's a change in energy. So the work done must have changed the energy of the pulley itself. Okay, so if we imagine the pulley now has an angular speed, and every particle on the pulley has a tangential speed. So if we start with kinetic energy. This is like translational kinetic energy. This V applies to any one particle that is part of the pulley. It doesn't matter where it is. And so by rotating an object, we've given all of the particles translational kinetic energy. They're rotating around an axis, but they're moving in a linear fashion, or in an arc in this case. Now, I'm going to apply another translation. The speed that that particle has is equal to its distance from the axis times the angular velocity of the entire pulley. So I'm going to make this substitution and say that the kinetic energy of of that particle is equal to 1/2 times its mass times its distance from the axis squared times the angular velocity squared. A little rearrangement. In other words, I'm just going to group a different set of variables. And the kinetic energy of that particle is equal to 1/2 times mr squared times omega squared. Mr squared is what we know to be the rotational inertia of an object or a system. So what we can then apply is we can like add everything up. We can say if this is the kinetic energy of one particle in that pulley, then the kinetic energy of every particle in that pulley is going to be equal to 1/2 times the rotational inertia of the whole pulley times omega squared. And so our new type of energy is just an extension of something we already know about. Rotational kinetic energy of an object with shape, or an extended object, whichever phrase I've been using on a given day, is equal to 1/2 I omega squared. And so this is the analog of kinetic energy for something that's rotating. And this describes an entire object instead of just a particle on it. This is also in joules. And so what I wanted to do was just solve a problem with you for rotational kinetic energy. So the rotational work, we're really just deciding whether there has been a change in energy. This is really the focus of this part of the unit. Okay. So we're going to imagine a pretty simple scenario, much like we did in the energy unit. And we have an object that's going to roll down an incline. That object is no longer going to be a particle. It's going to be an object with shape. And so this is going to be a tennis ball. The tennis ball is going to be released from the top of a ramp, and that ramp is going to have a height h. And the question we are going to answer is, what is the speed at the bottom? And so the conservation of energy works the same way, except now we're going to have to utilize this other form of kinetic energy when we think about conservation. So everything else is still the same. This is an object that's at the top of a ramp. So relative to the bottom of the ramp, it has gravitational potential energy. What's different is by the time it gets down to the bottom of the ramp, two things are happening. Obviously, the ball has moved, and so the center of mass has a speed, and so there's kinetic energy. We're going to call this translational kinetic energy. And because a tennis ball would roll down a ramp naturally, the tennis ball also has an angular velocity. And so in addition to translational kinetic energy, there is rotational kinetic energy. And so that's really the big difference here, that we have two types of kinetic energy and an object can have both. The important thing here is like the center of mass of the ball had to start moving and is now moving faster. And so that's why we have translational kinetic energy, that the center of mass is in motion. We also have rotational kinetic energy because every particle in the tennis ball is rotating around that central axis. Okay, and so we're going to apply this understanding to find the speed at the bottom. So I'll put that into an equation, and we will start working with it just like we have. And so this tennis ball, we need to know a couple things about the tennis ball. The tennis ball is going to have a mass m. It's going to have a radius r. And a tennis ball falls under the category of a thin spherical shell rotating about its central axis. And so it has a rotational inertia equal to 2/3 mr squared. In a conservation of energy problem like this, knowing that equation for rotational inertia is really imperative. And like some physics magic happens in a minute. All right, so we start with gravitational potential energy. So that's m times g times the height it started at. Translational kinetic energy is going to be 1/2 times m times v squared. So we're going to find that value v, plus 1/2 I omega squared. Okay, so it's not every problem, but in this problem and similar problems, the I omega squared is something you're going to need to substitute with. So we need to use this expression for I. Basically, because we don't have a value for it, we need to use the equation for it. And then as far as omega, this is an object that's rolling. And for now, we're assuming objects are rolling without slipping. And so what we can do is we can say that that angular velocity is equal to the speed of the center of mass divided by the radius of the ball. So I'm going to substitute both of those things in right now. So mgh plus 1, nope, not plus, equals 1/2 mv squared plus 1/2. And then we have 2/3, I'm not doing a good job copying here, mr squared and then times v over r quantity squared. All right, so we've expanded the rotational kinetic energy to include the expression for rotational inertia and the translation between angular and linear quantities. Look at what happens. There is now mass in every term, and so I can cancel that out. In theory, this means that the mass of the tennis ball doesn't influence its motion. We can test that in class. The other thing that happens is if you look at what's happening over here, r squared is over here in this term, and then 1 over r squared is going to pop up in that term. So the radius of the tennis ball also seems to not matter. We can test that in class. Now I want to be very careful and make sure that I've got everything that hasn't canceled. So g times h equals 1/2 v squared plus, okay, so 1/2 times 2/3 is 1/3. And then the only thing left is v squared. So this equation simplified greatly. All right, so I have to do some combining of like terms. So g times h equals, all right, one common denominator is going to be 6. So 3/6 plus 2/6 is 5/6, and then v squared is left over. So in the end, my speed at the bottom is going to be the square root of 6/5 g times the height of the ramp. We get these like nice little expressions that seem to only depend on the fraction at the start of the rotational inertia equation, and then g, and then the height of the ramp itself. And so that's just one example of how energy comes into play. I'll let you get started with the problems, and then when we check in later in the week, we'll talk about rolling with and without slipping.